is the last lecture. I cannot shut down. Okay, again, you can hear me clearly.
Yes, sir, we can hear you.
Okay, then first of all, I will make a short summary of what we have discussed in the last lecture. We started. Let's switch back. Again, we started with the antennas based on metallic surface. Wait, I have to look for your guy. And this was, for instance, an antenna array based on these metallic elements, in this case, waveguides. Also, for instance, in this Boeing reconnaissance aircraft, you can see it here in this radome. It's very large. And also we can find it smaller arrays in the Mikoyan Gurevich 35 and also in this civilian aircraft as a weather radar. Then we looked to another type of antenna. It's a very cheap and very flexible type of antenna based on PCB. This is the so-called microstrip antenna. And I showed you some fundamental configurations and some types: square antennas, rectangular, circular antennas, and also some different feed possibilities. Here we have a coaxial feed, goes through the ground plane over an iris. It's a, let's say it's a edged hole, and then with the inner conductor, because the substrate it's not very thick, it's only 1-2 millimeters, or sometimes smaller, depends on the frequency and the permittivity of the material. Then it goes through. Normally here is a solder point, but it's with other techniques connected, or without galvanic contact. This here is a galvanic contact, and here we have radiation contact, means not non-galvanic. It's a aperture coupled feed. There is a slot here in the ground plane, and through the slot, excited by a microstrip line, we also can excite this gray upper patch. And the other possibility was here the proximity coupled feed. It's only a microstrip line based on the ground here and excites the patch on a second substrate on the surface here. Okay, some formulas to calculate the input impedance using these different feed possibilities. And now I also showed you how we can excite such a square patch with or in such a way that we can excite circular polarization. And let's say the key element feeding such a square patch antenna is a so-called 90-degree hybrid. And if you want to have left, or in this case, right-handed circular polarization or left-handed circular polarization, depends only if you feed the hybrid at this port or at this port. phase difference between the two outs. It's in every case 90 degrees, but we speak only about a phase difference between these two ports. We assume, for instance, feeding here, it's, let's say, 0 degree, and here 90 degree plus 90 degree. Feeding here, it's the opposite. And so we have different rotation of the E field vector rotated by this square wedge. Yeah, this was only an example showing the influence of the thickness of the substrate and also the permittivity. We know that the smaller the thickness, the smaller it's also, for instance, the efficiency and the bandwidth. And the lower, this was the antenna with the high permittivity, and also the lower the permittivity, here we have air, we also can show that we have the higher bandwidth, the higher efficiency of the antenna. And it's clear it's overlaid with the thickness. Large thickness and low permittivity results in the highest bandwidth and in the highest efficiency. And this is shown in this example, or was shown in this example. Okay. Next slide. Instead of, let's switch back, instead of using such a hybrid because of its additional effort, additional network it's necessary here, we can also use other possibilities to excite circular polarization. The right hand it's shown here, left hand it's shown here, means the phase difference between the two edges here, it's made internally with this slot in the antenna. You can see here, if we turn it by 90 degrees, so that also the feed point is here on this side, then it's clear that the slot in this patch, in this rectangular patch, it's perpendicular regarding this one. Means we use this patch slot in this direction, then we have the left-hand polarization. Another possibility is also to cut the edges here. Depends on the location of the feed point. If the feed point, for instance, is laying on this point 3, then we have, let's say, a right-handed polarization. And if the feed point is located on point 1, then we have left-handed. Another possibility is here. This elliptical shape of a patch antenna to create circular polarization. Then we go further and we are touching the problem of antenna arrays. And here we can see some configurations of, let's say, group antennas made by such patch elements. And here this was a group antenna consisting of subgroups, let's say 2 by 2, 1, 2, 4, 3 such subgroups of 4 elements or 2 by 2 elements. And then I showed how we can feed. This is the feed network or the feed lines. All these strips here are in principle micro strip lines. And we have to consider some special conditions, because if you connect 2 antennas here, then it's clear that at this point here, or at this point, it's the same problem. We have only the half of the input impedance. If this is 50 ohm and this is 50 ohm, and we connect this with 50 ohm line, then we have here only 25 ohms, it's clear. And so we have to insert, for instance, transformers to make from 50 ohm, for instance, along the transformer line, for instance, 100 ohm. And then at this feed point, we have, again, because of the parallel connected elements, again 50 ohm. And all the things we have not discussed, but I only want to mention it so that you know it's not so easy to design such a group antenna or an antenna array. Yeah, then here we have the base problems of the antenna arrays shown on hand of the microstrip, a single element. And we found out that we can here, in case, or as a very simple example, based on very small dipoles, in principle Hertzian dipoles, located along the z-axis, then we found out that we can calculate the overall performance of such an antenna by this, let's say, base formula. We know or have to know the radiation behavior of the single element multiplied by the so-called array factor. And this is shown here. This is the single element. It's in this case valid for the very short or more or less Hertzian dipole. I look again to the eta here. It's the free space wave impedance, 120 p ohm. Don't forget it. And here, this is the dependence on the angle in the free space. And here, this, you know, it's our current distribution along the dipole. But because we have a very short dipole, the current is a constant, and so it's only the sum of all these single currents of the single dipoles expressed by the index n. And in case of a two-element array, as an example, you can see it here. Here we have the two currents along the dipole. In this case, the dipole is not an Hertzian dipole, or it has a certain length, for instance. And now we can see what happens if we look to the diagram. This is the single element. Then with a certain distance between the, sorry, this is not a single element. This is the distance between, we have two small dipoles in a distance of 0.25 lambda, or force wavelengths. Here we have a half wavelength. For ambiguity, it's normally this the threshold. This is the borderline. And if we exceed this, then you can see we have here also we have here 0, it's clear, and then we have here the so-called grading lobes. If we go out of or larger, the distance is larger than a half wavelength, then we create a second lobe or beam or side lobe, which has the same magnitude or value than the wished main lobe. And this is a problem why we have to avoid, if we have a lot of elements, to make the distance larger than a half wavelength. Then we achieve here ambiguity effects and generate additional so-called grading lobes, means additional in brackets side lobes which are non-wished. Okay, this was the summary of such an array discussion. Then we had a discussion about the amplitude distribution of the single elements in the frame of such an array. We can apply different magnitude distributions of the single elements, for instance, after Chebyshev, or another, its distribution could be the Taylor distribution, but in every cases we have to take into account that the overall, let's say, beamwidth will be wider. Okay, we can reduce the side load levels, for instance here, down to minus 30 dB, but we have to pay this with a larger half power beam width. And here we have some examples. Here we have over this array 8 by 8 elements, means 64 elements completely. We have the well-known side lobe level. If all elements are excited with the same magnitude of the 13 dB, what you can see here. This is the first side lobe, the other ones are smaller. And you can see if you use a high permittivity material, and in this case we have a very large frequency, 28 gigahertz, it's a millimeter wave antenna, then the patch has only such geometry, 52.5 millimeters in square. It's very small, and we can achieve at least a gain, and then you can, by the area factor, you can calculate the gain, as we know, by go down to 2 exponent x, it's 64, and 2 in log scale, it's 3 dB, and x, it means I have to multiply it with x coming from the area factor. Okay. Here, I showed you additional, if I want to make, let's say, a steering of the antenna beam, then I can do the following. I can excite all elements with different phase. If we start here, lower left corner, let's say with the phase assumed as or defined as 0, then all elements in the x direction and all elements in the y direction has to follow, for instance, such a formula. Or you can think about what is to do. If you want to have a certain steering angle, then you know that, for instance, if you use only 2 elements, from the one to the next element, you need, for instance, 30 degree in phase difference. Then from the first to the second element, 30 degree. From the second element to the third element, you also need 30 degree. From the third to the fourth, 30 degree, and so on and so on. And the same rule in the y direction, 0 degree. It could be, for instance, 30 degree, but it also could be here 0 degree. What does it mean? If the phase difference in the y direction is, for instance, 0 degree, then you only can steer your main beam in the x direction. If you apply also phase differences in the y direction, then you can steer the main beam in the x direction and also in the y direction. And this is what is expressed, or what is shown with this, let's say, formula to feed the single elements. You can also think about by yourself what is to apply, that at least the main beam looks in a certain direction regarding the area normal vector standing perpendicular to the plane here of the antenna. And here it's such an example in the y direction. We fed all the elements in the y direction by different phases in steps of, for instance, 10 degree, and then one times the antenna looks straight in the sky, and then here you have the other angles depending on the phase exciting the elements in the y direction. Okay, this was a special example to create with a very simple 2x2 array here. It's let's say a 2 different frequency patch antenna, but it doesn't matter. let's assume we have only 4 patches here, and with this or with such a network, you can achieve 4 different patterns at the same time. But you need, it's clear, also in parallel 4 different feed points. And here you can see the different feed points, so that you can have, and also we have additional the possibility to change the orientation of the circular polarization, left and right-handed, and so we have a very high number of feed points which are necessary. Okay, this was realized at the university in Ilmenau, in the center of Germany, and for receiving GPS and Galileo satellites. Yeah, and this was our starting point, or is our starting point for today's lecture, the antenna measurements. I already gave a short introduction based on this slide here. And so let's proceed with the antenna measurements. I started with the idea, if you have here the antenna under test, or our sample of self-designed antenna, and now I want to measure the pattern, the radiation behavior. So you can use a probe antenna with a detector and try to go around the antenna, and then you will see, depends on the frequency and the conditions, means you have for this measurement in every case to fulfill the so-called Fraunhofer, or you have to hold the Fraunhofer region, or you have to keep the far field condition. You know, it's 2d in square divided by the wavelengths. D in square means the distance between 2 points which are, let's say, showing the contour or the aperture of the antenna. This are the largest points, or the largest distance of points, of 2 points, which described or laying on the contour of an antenna. Maybe it's a dish antenna or a wire antenna and so on. This determines this, for instance, in the formula, this large D. Yeah, and if the wavelength is, for instance, very large, then it's clear that because only of the large wavelengths, your measurement distance, it's also very large, and so you have to hold this distance, let's say 2 wavelengths or 3 wavelengths in case of a wire antenna, and then the problems are starting, because you have also go up in height, and then you have to realize the measurement condition. For instance, the radius or the distance from the antenna under test, you have to be held constant at every point. And if you go only, let's say, with a normal handheld measurement system around this area of the antenna, then you can go around in a certain circle. It's no problem. But if you have to go up in the height, then the problems are starting. You need additional things to come in a height of, let's say, here at this z-axis, let's say of 100, 200 or 300 meters, and this is not very convenient, not comfortable. And what can we do to overcome this problem? And I mentioned it already. You turn the antenna on a test around or against your observation or measurement point. But that means the probe antenna with detector, it's located on a fixed point, and then you can turn the antenna under test in all directions so that you can measure the pattern. And this is shown here. Let's say here we have the plane, a measurement plane. It's not necessary that the plane is, let's say, a metallic area. It should be an area without reflection. That means the best thing is if this plane is, let's say, an absorber, which collects all the radiated electromagnetic energy. This is in principle given in case of let's say, large wavelengths in the free nature. But on the other hand, you can, then we will see this later, put the antenna on a certain height so that the influence of the ground it's not so dramatically. Yeah, here is the measurement principle again. You have a generator with a, let's say, illumination antenna. This is our antenna under test, or test antenna. Far field condition is fulfilled, and here you measure the voltage at the connect between these two connectors, voltage A. So and you turn this antenna, you see this with this arrow, and then the output voltage over this angle. This is our pattern, what we want to know. And again, if we turn the antenna here in the plane, this is in the phi angle plane, this is the azimuth. And if we turn the antenna in this direction in the plane of the z-axis, then we speak about elevation. Now, if you have measured some pattern, for instance, in one measurement plane, in the elevation plane or in the azimuth plane, then if you make here you have the angle of the antenna, the turned angle. Let's say this should be the elevation angle, and then you have here your voltages. Yeah, if the voltages are scaled linear, you can see here the pattern. And in some cases, you have very small voltages, and then here it's not, or you can guess it could be a zero, but it's not clear because the resolution is not very high. And if you scale this in the log scale, you can see here that the resolution in the low area is much better. You can see here that the pattern in the logarithmic scale, you can see here the two side lobe levels. These are in the graphic much higher, and then you can see here minus 30 dB means we have very small voltage here, and this you can define this as the first zeros in the elevation range, left and right besides the main lobe here. This is the logarithmic scale. It's, as you can see, good. It brings an advantage in case of measurement systems, because then you can in the sketch realize a much higher dynamic range in comparison with the linear scale. Okay, then here in this figure you can see how you can normally measure an antenna or an antenna system. On the left side, this is the illumination antenna, and on the right side, this is our antenna system under test. And means we have to realize the possibility that we can turn the antenna around this axis or around the azimuth plane or phi plane, and additional that the antenna can move in this direction, means in the elevation plane, in the theta plane. And what is additional shown here? I mean, the antenna should be very high. The antenna on the test should be very high mounted over the ground. Also the illumination antenna. And we have two towers here, for instance. In earlier years, these towers were made from non-reflective material, for instance, dry timber or dry wooden material or plastic material with a small permittivity, so that we have from around the antenna on the test we have no reflections, and also we have no additional reflections from our illumination antenna. If the illumination antenna, let's say, is not has not a high gain or has not a small half power beam width, that means the antenna also radiates behind her main beam. You know, she has a limited forward back ratio, and all the radiation which is not concentrated in the forward direction can go out in this direction and can cause reflections, which also can occur at the receiving antenna. But in this case, it should be the forward back ratio should be very good. Means the electromagnetic radiation is concentrated by the illumination antenna in this forward direction. But what you can see here additional, and this only occurs if the, let's say, the half power beam is it's large enough. Again, you can see it here. Then you also have side lobes, and also this side lobes, as you can see here, has a level. It's only a minus 10 dB lower than the main beam. And if, let's say, the illumination antenna has this characteristic, you can see it. This is 0 degree. It's the main beam here. And for instance, if you look to plus minus 180 degree, this is the back side, then we have a higher level. Means in this case, if the tower is, for instance, if the tower is of reflective material, this also can cause an additional radiation. But in our case, we can see here we have, let's say, plus minus 70 degree. We have 0, means this is 90 degree. This covers also the 0, means in this direction we have only, we have no radiation. Radiation is very, very small, lower than 30 dB regarding the main lobe. And if we look to another angle, let's say minus or plus 60 degree, means this is about 60 degree, and this angle here, let's say it's about 45 degree. Let's go to 45 degrees. This one means we have here a more or less great part of our radiation. Here the main beam is 1. It's normalized to itself. And if you go to let's 45 degrees, it's about here in this local minimum, but it's only, let's say, 15 dB lower than the main beam, and this is, for instance, only one ray which can reflect it here at this specular point, and also can receive our antenna under test. Means then we have a measurement error in the plane or at our antenna under test. And what is written here, the spherical waves deviate from a parallel rays with, this is the limit with a 22.5 degree phase error. It's a 16th of lambda at the distance exactly at R2. This is the d what I have explained before, d in square by lambda. This is the threshold of the far field. And at this threshold of the far field, we have already such a phase error for in the plane here, in the measurement plane of our antenna under test. And this is the reason why our measurement distance from the antenna, from the illumination antenna to the antenna under test should be much larger than this what is shown here in this rule. Means the distance is much larger than this value here, and so we can achieve that phase error in the plane of our antenna under test is much smaller than a 16th of the wavelengths. Yeah, what is, or how can we determine, or how can we let's say consider, yeah, how can we consider this measurement error by a reflection on the ground? Again, we have here our two antennas, illumination antenna, antenna under test, in this distance large R. And how can we consider, or how can we consider this measurement error by this reflection? And this is shown in this slide. Error in measurement due to reflections from the ground. Let's assume E with the index large D. This is the electric field at our antenna under test. This is, let's say, this is what we want to measure, or what we have measured, assuming we have no reflection. And then we have a small part which comes from the reflected electric field. This part along this way, and then we have the total field at the antenna under test. This is what is coming in from all the two parts together. It's coming in at the antenna under test. It's the total field. So what happens? We can write, for instance, the total field is the sum of our electric field directed or coming direct from the illumination antenna plus the part of our from the reflection on the ground. Or this is these two parts are vectors, and then we have to write it in as a vector. We can say it's the total field, it's the magnitude here by this angle of this electric field, and this is the direct electrical field. Here it's the magnitude, and here is the angle plus the magnitude of the reflected part, and here this is the angle. Now we have the problem that we cannot determine, or we cannot measure directly the angle of these vectors. We only can make two things. We can try to adjust the let's say, we can adjust the antenna or the angle in such a way that we either can have a maximum or we can have a minimum. And this is shown here. We can write this in this way. We have the total electrical field, the magnitude, divided or related to the electric field at the antenna under test. And it's only mathematics. And okay, if you divide this part of the formula by ED, then you have this one, and then Then you have here the quotient of the reflected part divided by ED, only the magnitudes. It's shown here, and it's clear because of the vector in the brackets here. It's the angle of the reflected wave minus, I have to look, minus the angle of the part of the direct wave. Yeah, it's clear because this was one is clear, and this is the angle difference. Yeah, and now we can make the following experience in our mind. We say if both vectors are in phase, then our formula, it's very simple, given by this value. This is the maximum what we can achieve. Means the one is clear because of the division, and here we have only the magnitude from these parts because the angle difference it's 0. And so this is the maximum. And now if we look to the possible minimum, then it's clear we have only the opposite. It's 1 minus this value. This part of our measurement results, it's unwished. It makes the error, and it's pendling between this value and this value. And if we only look to the error itself, then we can assume it as this quotient. It's in dB is nothing else than the quotient in linear scale by 20 times decade logarithm of this value. Then this is our measurement error. Another problem what we can have in case of measurement, the elevation angle. As you can see here, it's our transmit antenna, the direct pass. Here we have the reflection as discussed all the time, and then we rotate our antenna under test in the elevation measurement plane. So we can have the problem that in a special case, the main beam of the antenna under test looks directly in the reflection path of this reflected on the ground wave. And so our measurement result, it's more or less higher, not higher, it's more worse. And here, if the antenna is turned in such a way in comparison of this scenario, then we can have here, as you can see here, a 0 in our pattern means that the reflected path has no influence in our measurement results regarding the pattern. And then here we can measure exactly over the direct path in this small angle range, we can measure the side lobe. If I switch back, we assume we have such an antenna here as an antenna under test. Means we have here the zeros in the range of, let's say, between 7 and 90 degrees. Sorry. And then this is about this, or roughly this should be this angle, let's say 45 or 50 degrees. And if you have here a 0 or a very small, very small side lobe level, then the influence on the measurement result is very low. But nevertheless, if you have this this part of reflection, the measurement results, it's not exactly, and it's a little bit worse. And this is shown here in this graph. Here we have the quotient of the total field strength, the measured total field strength at the antenna under test, divided by the direct value And if the reflection is very small, we can start here, means this value, this quotient, it's shown here on the y-axis, it's very, very small. And so if we look, for instance, to an error of -1 dB, it's shown here, then the reflection, you know, this part here, reflection, the reflected field, or coming from the reflection point divided by the direct field strength in dB, occurs already if this value it's a little bit larger than -20 dB. Let's say it's about 90 or let's say 90 or 80, 19 or 18 dB. Yeah, if this is already in this range, then our measurement error it's already -1 dB. And if this contribution is growing, means the reflection is growing, then you can see here we are pendling between an error of, in case of -10 dB, of minus 3.5 about, or if the contribution is 1, then we have two cases. If the depends on the phase, and so we have two different curves here. The upper curve, the solid curve here, shows if the contribution it's 1, means 0 dB in log scale, then our measurement error it's 6. It's clear because the direct field strength plus the reflection part has the same value, and so our measurement result it's much worse. You can see this here. And if the contribution it's 1 or in log scale it's 0, then if the phase it's on the opposite side, here this is valid for a phase of let's say of 0, and here the phase is opposite, so that we have the difference between these two contributions. Then we can see that our bounce or threshold to the measurement result is much larger, and this is the reason why we have to look for the reflections on ground in such a way that the contribution of these reflections is more or less, or should be lower than 20 dB, lower than 20 dB, or smaller than -20 dB. This contribution of the ground reflection. If it goes in the direction of 1, then we have very large measurement errors, and so the pattern of our antenna, it's not used. We cannot use this. To overcome the ground reflections, you can see here a measurement setup shown in this sketch. We have the ground, we have only one tower. This saves material for the second tower, and our transmit antenna or illumination antenna is also mounted in the near of the ground. This means in this case the antenna is not touching the ground. It means only that the antenna is located in the near of the ground. The non-metallic tower or the mast should have such a height that our our far field condition is fulfilled. Also here, this measurement distance has to fulfill the far field condition. This is very important, otherwise we also have very large measurement errors. Okay, In all these cases, the source antenna or illumination antenna should be directed towards the test antenna, and otherwise we reduce the so-called dynamic range. It's clear if the antenna for illumination looks not directly to our antenna under test and shows, for instance, a value in the pattern in a near of a zero or of a side lobe, then the so-called dynamic range it's not full, means we cannot measure in special cases the deepness of a zero. We only can see that the measurement receiver goes down in to the noise floor. And again, the spherical waves from the source antenna cause a phase error across the test antenna. It extends or means the same if you extend the D that behave exactly as the far-field distance phase error, what we have discussed. What does it mean? We cannot apply here an antenna under test with let's say a larger D which oversees the far field condition. This is let's say a special problem if we have, for instance, smaller wavelengths in the gigahertz range, and you have, as you know, large dishes to receive signals from the space and so on. And such an antenna with a large diameter or a large aperture, this is given here by the D. If this is large enough, then we have the problem with the phase error, or in other words, this measurement distance here limits this large D, the diameter of the aperture, diameter of the dish, or the extension of the antenna between the largest metallic points away from each other. Now, in the slides before, we discussed about antenna measurement systems normally localized in the nature. And if you measure in the nature, it's clear that we cannot, or we have to look in the sky. Means if there is rain or snowfall, then this natural things or very strong influence the measurements of our antenna system, especially at higher frequencies, especially rain and also snowfall influences very dramatically our measurement results. And so we had to wait if the weather is fine. Also, strong wind can influence the measurement results because, let's say, special antenna configurations with a certain, let's say, with certain dimensions are sensitive to strong wind because they have a high wind withstand, so that they can vibrate, like because of wind impulses. The antenna can vibrate, can move a little bit, and especially in case of high gain antennas, this small movement also influences our measurement results. So that we also, under these conditions, we have to look before we start such a measurement in the nature. We have to look for the weather, and if the weather is fine, very small wind, no rain, no snowfall, and also in winter time, it's also a problem. If you can have sun, you have no wind, but you have snow on the ground, and you know what we have discussed. Snow on the ground increases the reflection potential for this not-wished reflected ray of our electromagnetic wave, so that we have an increased capacity or increased value of this reflected part. And to overcome all these problems, we are in a lot of industrial or military measurement test sites, they go to test chambers which are installed in a room or maybe in a large hall, or in other words, to keep out the influence of weather. No rain, no snowfall, no wind. This is the reason why in a lot of cases such antenna test sites are installed in rooms. But in a lot of cases, depends also on the measurement scenario, depends on the antenna you want to measure, depends on the working frequency range or the wavelengths. It could be that if you only use the same scenario, what we have used outside in the nature, this measurement scenario, let's switch back. For instance, this scenario, what we have discussed, or the scenario with this tower. Also, this tower, it's let's say limited in a hall, and then you have here the ceiling in a hall or in a special room, and also you have problems with reflections around the antenna under test coming from the ceiling. And so if you use this test site or the test scenario in a room or in a hall or whatever in a building, then we have, for instance, one possibility to reduce the given distances by the building, by the room, or by the hall. Here, this is shown here. If you have a limited distance from the antenna, which illuminates normally the antenna under test, then we have here a reflector with a certain shape. The reflector with this shape, it's layout or designed in such a way that from the illumination antenna, you have to know the characteristic of this illumination antenna, that the outgoing rays here are in parallel colliminated. And so at the receiving plane of your test antenna, you have a phase planar receiving field of electromagnetic waves. And this is exactly what you want to have. And with this scenario, you can very strongly reduce the measurement distance in regarding to the test scenario. For instance, what we have shown here between two towers. And this is named here a so-called compact range test setup. This is it's not so easy to realize, but at least it has the advantage that you are completely independent of weather and all these influences what you have in the nature. And also you can reduce the necessary, with this technique, the necessary measurement distance to ensure the far field condition. As you can see here, the problem what we have in case of the spherical waves coming from our illumination antenna, this is let's say repaired, or it's compensated by this special shaped reflector. And this is the secret, let's say, secret of this compact range test setup. The advantages are you can use, in this case, smaller rooms than in case to realize the far field condition with the help of this offset reflector. The diameter of this reflector, this is, let's say, that in a certain range, a disadvantage, should be larger than about 20 times the wavelengths, and to realize the so-called quiet zone. Quiet zone means this is the zone in which you can achieve, let's say, special measurement results. No, you can get measurement results with a certain error. Let's say if the magnitude error given by you, it's, for instance, minus 30 dB, then means in this zone, which realizes the magnitude error of minus 30 dB, this is named quiet zone. If you use another level, let's say you are sufficient with minus 20 dB on measurement error, then in the same test setup or in the same test scenario, your quiet zone is larger. It's clear because you have, in this case, a higher tolerance against measurement errors. This is, this is the idea of this so-called quiet zone. This is valid for magnitude errors and also valid for phase errors. The quiet zone is determined by a threshold of magnitude errors and also of phase errors. For instance, you can say I have measured the antenna in the so-called quiet zone with a measurement error of plus minus 1 degree. This is the second value or second threshold of this quiet zone. The room itself normally need not be with absorbers to avoid reflections, but in every case it's better to have absorbers. Okay, because if you have here your test antenna or antenna under test, and here in the background there are no absorbers, then also you have reflections of the wall. Okay, if the reflections, if the plane of reflections is exactly or has exactly the same plane like your antenna under test, so that the reflected rays are exactly the same like the outgoing rays here, then the measurement result should be okay. But nevertheless, you can see if you have here in this plane reflections, and you have to measure the so-called forward and back ratio, then you also have from the back a certain amount of reflections. And this is the reason why you have to install here in this plane on this wall absorbers. And in the next slide, we will see how such an absorber looks like and what is the issue of such an absorber. Here we have the two problems in far field range. We have phase error problems. You know, this is the condition for to go out of the Fraunhofer region. What we have discussed exactly at the Fraunhofer region, we have the phase error. It's a definition coming from the past of a 22.5 degree. This is the allowed phase error for far field condition, but we want to have a smaller phase errors, means we have to go in a larger distance. And this is for, let's say, measurement system which uses the two towers and do not use the compact range, or better, in other words, it's the classical antenna test scenario. And in case of the compact range, then we have magnitude or amplitude errors. Why? If you look there, here you can say if we add the distances here or the lengths of this vectors, it seems to be it's the same, but you have across this plane or across in this plane you have, let's say, very small phase errors, because you can compensate this with the shape of this reflector. But here because of the very large area of this reflector, but the pattern of our illumination antenna here, which illuminates the reflector, then we are not or we cannot illuminate this exactly over the half power beam with the same magnitude. If you have here an antenna, illumination antenna, which illuminates this reflector, then over the let's say over the necessary illumination angle, you have a magnitude decrease. To show this again, here, look here. Let's say the opening angle should be in this range for illuminating our compact range reflector. Then you can see over this angle here we have a very large variation of magnitude. This is one of the reasons why we speak about now here as a problem in compact range. We have amplitude errors, and this is not so easy to compensate. You can use an antenna with a very wide half power beams or a very large opening angle, but at this race, you cannot avoid a certain magnitude difference. This is physics. Here we can see such a compact range test site with absorbers. This is a cross section. You can see here the reflector for compact range, our feed antenna, in this case, for instance, a Hall antenna, and we can apply such a Hall antenna which has, let's say, a more or less large opening angle, and all reflections are coming, for instance, from here. This is our columnated beam from the shaped reflector. Without this absorbing elements, then we had a strong reflections directly from the backside of our antenna test. And to avoid this, we have here on this wall this large absorbing pyramids. This pyramid consisting of a special material. It's a foam-like material and filled with particles of ferrite material and with very small particles from carbon particles and ferrite particles are mixed in a special relation to each other, and it's the foam from, I don't know, plastic material or whatever. It's filled with this particles, with this carbon particles and the ferrite particles, and then it's realized with external gas, and then you can make a foam from this material, and from this final, let's say, foam blocks, then you can cut out this absorber pyramids. Depends on the wavelengths what you have to apply, or the measurement frequencies. It's clear, the longer the wavelengths, also the larger the height of this pyramid absorbers. If you use very high frequencies, 1 gigahertz and higher, such pyramids are in the length of about, let's say, 300 millimeters. If you go in the frequency lower, down to, for instance, 100 megahertz, is the frequency of ultra shortwave radio. Then the observers have a length of about 1.5 meter, and or minimum 1 meter. The length depends also on the amount of the reflections. The longer the pyramids, the lower the reflections. Okay, this is what I want to say you additional. And here, our measurement system for the antenna under test consists of a positioner, and this positioner allows to turn the antenna here in the elevation plane, this plane, or it turns here the antenna in the azimuth plane. And it's shown here in more detail. This antenna positioners, for instance, in case A here, it's named elevation over azimuth, or azimuth. Elevation over azimuth means elevation means this is the first possibility to turn the antenna in elevation. This is this plane, and after that you can turn it the antenna. Sorry, the first it's elevation. This is this turns, and then after this measurement you bring the positioner in position in this plane, and then you can turn the antenna in the azimuth plane. This is the azimuth plane. But first of all, the antenna is turned in the elevation plane. And here we have, in principle, the same, but it's named elevation positioner, and azimuth over elevation. This is the azimuth positioner, means the antenna is located in this, or the positioner is located in this plane. Then you turn the antenna in the azimuth, and then if the measurement is realized, then you can change the angle, the elevation angle, and then you can move it again. And so with these two different positioners, you can measure every point around the antenna. In principle, every point. In practice, the scenario of the measurement it's realized in such a way that you cannot use, let's say, a high density of angles, of measurement angles. Means you have to give the measurement engineer information that you want to have in elevation and in azimuth. You want to have, let's say, measurement points in steps of, for instance, 3 degree or 5 degree. The smaller the angle difference, the higher the measurement effort. It's clear. If you say I want to have it in 5 degree steps, then it's the measurement speed is much higher in comparison with you want to have it in 3 degree or in 2 degree. It's clear. Don't forget, this is every measurement of the pattern. It's realized for one frequency. You cannot sweep during the measurement the frequency or change the wavelengths. You have to choose, let's say, your center frequency, and then you go around all angles in steps of, let's say, 5 degree. Then you have the pattern at one frequency for all angles in the elevation and azimuth plane in steps of 5 degree. Now you change the frequency. The working frequency of an antenna, for instance, let's say in the range of the bandwidth of the antenna, the bandwidth. The bandwidth is determined, for instance, by the voltage standing wave ratio. This is let's say a more or less international agreement with a voltage standing wave ratio of 2 in return loss. That means in the return loss, in measurement of the return loss of minus 10 dB. or if you say return loss, then it's the measurement result is minus 10 dB. But if I say it's return loss means 10 dB, return loss means in measurement scale minus 10 dB. But if I say this is the return loss, then okay, then the loss is 10 dB return loss. Okay. Voltage standing wave ratio, VSWR, it's 2, and it's the same value in another measurement scaling of 10 dB return loss. So if the antenna works inside between these two values, then we speak about the bandwidth of the antenna. And if you want to measure the pattern in the bandwidth in this range, then you also have to give the measurement engineer some hints regarding the frequency. It's clear one measurement frequency, it's the center frequency. And then you can say, okay, the bandwidth is, let's say, 20 megahertz. The center frequency is 20 megahertz minus 10 megahertz. For instance, it's the center frequency. And then you can give him to the left and to the right of the center frequency, you measure, please, the pattern in steps of, let's say, 5 megahertz. Then you have at least the pattern in steps of 5 degrees at, for instance, 5 different frequencies. If this is sufficient for you, then it's okay, and it should be clear. Then you have a very large number of measurement results if you want to measure the pattern of such an antenna at much more frequencies. This is the problem of the antenna measurement setups. And let's go to a little bit simpler antenna measurement system. And this system, it's shown here in this primitive sketch. It's a so-called planar near-field test setup. What does it mean? This test setup, it's only, let's say, a cross-section. It looks like a scanner. Scanner for scanning sketches from a sheet of paper. And in principle, it's the same. It's the same mechanism, but only instead of let's say a laser diode or so, we have here a probe antenna, and inside this scanner, this probe antenna is moved along the X and also along the Y axis in steps of, depends on your resolution, and then the probe antenna has then a detector and a receiver with with a readout of the measured voltage, and this voltage is given to for instance, analog digital converter, and you can put it in a memory, the results at every point. And here you place the test antenna in a certain distance. This distance is given by the manufacturer of this planar near field test setup. But normally it's not very critical. All these things are very close together. For instance, they say, please put the antenna over a block of foam, of low loss foam material, for instance, polystyrene, in a distance of, let's say, 15 or 100 millimeter. And you can see here that such an planar near field test setup, it's very suitable to measure our microstrip antennas, because our microstrip antennas are flat, very flat constructions, and so this gain on near field test setup, it's very useful for measurement purposes of our microstrip antennas. And if you want to measure the back ratio, you only can turn around your microstrip antenna so that the antenna looks in the other direction. Again, you have to avoid any reflection, but the far field, the near field scanner can also measure the backside of the antenna if you only turn it around. And now you can ask how it works. If this if you place the antenna very close together to the probe antenna or to a probe system, then we never can achieve the far field conditions. We never can going out in the Fraunhofer region. This is correct, and you can see here how it works. We record the amplitude and phase values sampled by the receiving probe in the memory, and then we apply a fast Fourier transform algorithm, and this converts the near field pattern into wished far field patterns. It's a little bit complicated, this algorithm, but it was developed several years ago. But it's in principle one possibility to reduce further than necessary place of a room. Then with such an equipment, you can realize the antenna measurements again from microstrip antennas in a laboratory room. Okay, now where is my pointer? The gain comparison method, it's very useful to measure the gain of our antenna. In this case, let's switch back to an outside antenna. The pointer is visible, but I can move it with the mouse. And so we can measure the gain of our unknown antenna with this formula here. Sorry, I have to remove the mouse and again and hope it works. No, it works. Doesn't work. And then you can see here in the formula that the gain of the test antenna we can determine very simple by this. Okay, now we can make it in such a way. We have here our source antenna illuminates the both antennas either one after another. Means we have not used this switch. First, we measure the standard gain antenna. This gives our gain of the standard antenna, and we can measure or record the received power, PS, and then we exchange the antenna, and then we insert the test antenna, and we also measure power of the test antenna. And now to determine the gain of our antenna under test, then we can apply here this formula. That means the measured power of the test antenna minus the power of our reference antenna or our standard gain antenna cannot give us the correct result. It's clear because we have to consider the gain of the standard antenna. But as I mentioned, not only one times we can use such an antenna, for instance, as a dipole, a resonant dipole. We know the gain exactly 2.14 dBi, or we can realize, for instance, a horn antenna with special dimensions, and also we know exactly the gain of such a horn antenna. And if you know the gain of the horn antenna, or if you know the gain of our standard gain antenna, then we can very simply calculate the gain of our antenna under test. Yeah, if you use the two antennas in parallel, then you have to consider that the antennas influence each other, and so in practice it's better to use the antenna. Not in this case, you don't need a switch, you only put first the antenna, the standard gain antenna, in the test range, and then you exchange it by the antenna under test. This is the normal it's the normal measurement situation. We do not need here this switch. And here you can see a very large building or measurement room. It's not a compact range. You know, the compact range has the advantage. We can, it's also coming from the name. We can reduce the distance between antenna under test and illumination antenna, but the disadvantage is the magnitude error across the measurement or in the measurement plane. And so here, in a lot of cases, that scenario in-house is applied. We have here a so-called anechoic chamber. It's the same like what I have shown you in case of this compact test range. The anechoic chamber is also completely around all walls, placed with this absorber material or absorber pyramids, and so to avoid any reflection from the ground, reflections from the ceiling, and reflections from the walls. And you can see here, I already mentioned this, the antenna under test, it's placed in a special scenario or in a special distance against from the wall and also against from the transmit antenna. Yeah, you know, the distance here is much larger because to fulfill the perfect condition, and also the distance from the walls has a certain value to achieve this so-called quiet zone. This is a zone around the antenna. You have to imagine this zone. The zone it's given by the measurement errors, and only in this area you can achieve a certain, more or less certain measurement errors, low measurement errors regarding to that what you want to have. Yeah, here it's clear this is the elevation plane. Sorry, this is the azimuth plane in this direction, and if the antenna is going up and down, it's the elevation plane. And here you can see pyramidal absorbers, transmit antenna. Also the mass here, it's a dielectric material or dielectric base in both cases here. Yeah, then normally this is such a either a special measurement chamber as an, let's say, separate building, realized for instance with bricks, or it's in a room in a large building as a anechoic chamber. Okay, then as a summary, you can say we have here, in case of the anechoic chamber, let's say this anechoic chamber, it's very, very widely used. And we have controlled environment, means we keep out the weather, or in other words, it's all weather capability. It gives us a high security and minimizes electromagnetic interference for the measurement, because we keep out also radio waves coming from outside. For instance, if you make measurements in the nature, you cannot avoid that in your measurement scenario, or the measurement antennas also receives, besides ground reflections, also receives unwanted signals coming from outside. All these signals or influences your measurement results. It's clear, and this is the reason why a lot of, or in a lot of cases, you especially in Western Europe, which we have countries, for instance, like Germany, with a high industrial environment or high industrial um, environment. So a lot of, for instance, companies also produce distortions with a wide electromagnetic spectrum, or you have a lot of radio stations and so on and so on. What I want to say, you have a lot of unwanted electromagnetic radiation, and if you measure, or you want to measure your antenna in such a scenario, then it could be it's impossible to make measurements at certain frequencies, because from outside they are working at the same frequencies what you want to measure. Yes, and this is one of the problems why they use this anechoic chamber, and to keep out radio signals from outside. This is shown here. This is the metallic housing, or another name, Faraday cage. So this metallic, for instance, it's a grid, copper grid shielding, and this keeps away our radio signals coming from outside, from other radio stations, and working at the same frequency what we want to measure in this moment. Then you can say, okay, then if you want to measure the pattern of an antenna at the same frequency coming from outside, then we can use this radiation for the antenna under test. But again, then in a lot of cases, it's a distortion, but the signal strength is not large enough to measure the antenna under test with this necessary dynamic range, means the deepness of the nulls and so on. It's not sufficient if you use only unwanted signal working at the same frequency from outside. Then the controlled environment, we discussed it, security and so on. And then the inner surfaces are lined with, or inner walls are lined with RF microwave pyramidal absorbers. So it's clear, I explained it. And again, the length of the absorbers, foam filled with carbon particles and ferrite particles, determine the low cutoff frequency of this test chamber, of this anechoic chamber. And then the quiet zone, again, amplitude and phase of the incident plane wave from transmitting antenna. This should have very little variations, and here you can give such a threshold for a quiet zone, 0 dB in magnitude variation over the measurement plane, and half degree, 0.5 degree on phase difference. For instance, means from this point to this point, you have a phase difference of 0.5 degree, a half degree, and in parallel, the magnitude change is only 0.2 dB. Yes, this is the given as the threshold, or as the the error threshold to determine the quiet zone. If you go more inside a little bit, then this values are smaller. That means the measurement results are better than coming from these values here. Okay, this was the last slide regarding the antenna measurements, and it's at least only, or it was at least only more or less an overview, and I hope you could understand a little bit what is, or what are the problems or the results of this antenna measurements. And yeah, if you are a radio amateur, then it's clear that you cannot use such a very expensive antenna measurement scenario like this anechoic chamber or like such a compact range. And also this planar near field test setup, this, let's say, scanner, in Germany, you also have to pay for such a system together with the necessary software, about more than 50,000 euro for such a measurement setup. And it's only to show you or to give you an imagination what goes around this antenna measurement systems. Okay, now we have to start, or we want to start with the fundamentals of noise measurements, and then this is in our next not seminar, in our next lecture next week. It's the final point, and then we also I will come to the problems regarding the antenna, why an antenna also has to consider noise, or in other words, it's an antenna, a noisy device can produce an antenna also noise. And we can say in principle, yes, also the antenna itself can produce noise inside. It's thermal noise. And additionally, the antenna can collect noise from outside. In a lot of cases, the antenna for receiving signals, it's installed, let's say in the nature, it's installed outside, not in a measurement chamber. But also in the measurement chamber, the antenna can collect noise, namely thermal noise. And this is what I want to discuss in the next lecture. Now we want to look at, let's say, the basics of noise behavior of general radio receiving system. Let's start with this remarks here. Modern receiving systems has to receive very, very weak signals or very small signals. And under these conditions, if the signal is very small, then we come very close to the so-called noise floor, or to the noise level of the receiver. You can imagine you switch off the receive signal, or in other words, your transmit side switches off the signal so that you cannot receive any signal. What shows our receiver? Our receiver also gives out, let's say, a signal or a voltage, because the receiver chain has to realize a certain gain. Let's say 1,000 times, or 30 dB or 40 dB means 10,000. He has to, for instance, to gain 10,000 times an incoming signal. So if the wished signal from the transmitter is, let's say, shut down, switched off, then in the most cases, the people think then at the output of the receiver there's no signal. It's not true. We have a signal. This signal is, let's say, the noise. It's the noise coming from outside, received by the antenna, and then we have additional noise coming from the, let's say, the active elements, for instance, from our transistors. Every active element only works as an amplifier when it's driven with DC current. Otherwise, it cannot give amplification. And you look to a, let's say, a transistor. You also can look to a vacuum tube. All these two devices, in the past, the vacuum tubes applied for gain purposes to make an amplifier. And in every case, this works only under the condition that you can apply a voltage, then a current is flowing through the active device. For instance, in case of a transistor, it's the collector current, emitter current, base current. We have three different currents. Collector current, base current are adding to the emitter current, you know this. And in case of a vacuum tube, you have to apply a node voltage, and then you have a node current going out to the cathode, and then let's say cathode current. It depends on the number of gates. Yeah, at least you have also a current flow through a vacuum tube, and all these currents producing noise. And again, plus the noise coming from the outside, coming from thermal things, coming from the temperature of the environment. So here you can see a very primitive example of modern radio. We have here different modulated schemes or different modulations for the incoming signals. And this is a BPSK. It's only phase shift modulation, switching between plus and minus 90 degree, for instance. It's only two states. Here we have four states. It's named QAM. Again, these two signals have no modulation or no change of the magnitude. Only the phases switch. It means we have the same magnitude. Then this goes up to the state here of 8 different phase states, means all the signals have the same magnitude. Only the phases switch between smaller parts, smaller amounts. And here we have, for instance, an QAM means quadrature amplitude modulation. And here quadrature means we have a basic phase state of 90 degree, but we have additional magnitude modulation. Quadrature amplitude modulation. And here we have only a 16 phase shift between 16 states, also with constant magnitude. And here this broken line, it's with additional magnitude modulation, for instance, minimum also two different states. But what we can see here, here, for instance, it's given the so-called probability of error. Means if we want to receive these digital signals, we have to hold for, let's say, for instance, for clear speech, for a good picture, we have to hold a certain error of transmitted digital symbols. If we transmit per second 1 million symbols, then in this case we only can have one wrong signal per second in this, or this is the meaning of this value of this 10 exponent minus 6. per second means we have 1 million symbols per second, and only one is, of these symbols or one bit can be a wrong bit. And to hold this very good, let's say, error, probability of error, then, and this is shown here, then our signal to noise ratio means the signal what we receive regarding to the internal noise, which is produced by our active elements, what is produced by the thermal noise coming from the environment only over the antenna, then this signal to noise ratio must be better, minimum or better, for instance, let's say 12 dB. And if the modulation schemes are more complicated means we can transmit in a given bandwidth more information, more different channels. This we can realize with this higher modulation schemes. Then you also can see that the necessary signal to noise ratio, what we have to hold to realize this very good threshold of error. 1 bit is wrong regarding 1 million bits we are transmit. Then you can see the necessary to hold a higher carrier to noise ratio. It's evident here in case of this 16 PSK. This is a modulation scheme. It's for instance used in satellite transmissions, downlink and uplink. They try to avoid this QRM means try to avoid magnitude modulation But if you have no if you have no magnitude modulation, then the density or let's say the phase difference between the switching states, it's smaller and smaller, and it's clear that you have high demands regarding this signal to noise carrier to noise ratio here. It must be better or means it has to hold about 25 dB. The signal must be better or larger than the noise power. The signal power must be about 25 dB larger than the noise power coming inside from the system and the thermal noise around your receiver system. Yeah, and here in case of the BPSK, it's only, let's say, 12 or 10, sorry, let's say, yes, 10, larger than 10, 11 dB. And the difference between this modulation schemes here, in our case, is larger than, let's say, 14 dB. This is the range of this, which is covered by the different modulation schemes. Again, if you have a modern receiving system and you want to achieve a certain probability of error, then you have to also to keep or to hold a certain carrier or signal to noise ratio in your receiving system. Then the thermal noise arises from vibrations of conduction electrons. We say in brackets Brown's molecular movement. You know this, I hope so. And this causes noise by the environment temperature, and also the noise spectrum produced by thermal noise. It's nearly uniform over RF and microwave frequencies. We call this noise, it's a white noise. And this makes, on one side, the problem is easier because we know it's a noise power or noise level with a constant magnitude instead of the so-called colored noise. Then you have different parts with different magnitudes of noise. But on the other hand, we know this noise goes to infinity. It's not limited. The only thing what is limiting the noise is, let's say, the equipment around. If you say the noise produced by thermal environment is infinity, but we cannot detect it because, for instance, you need then antennas which also have a bandwidth of infinity, but this, from physical point of view, doesn't exist. So this is the last slide in our lecture today. The power delivered by a thermal noise source into a matched impedance. It's shown here. This is the Boltzmann constant. This is the environmental temperature given in Kelvin, large T, and B, large B, it's the bandwidth. And this product at least has the dimension, or the dimension in watts. And here again, Boltzmann constant, it's normally well known, but nobody can keep it in mind. Then this is our temperature. It starts with 0 degrees. 0 degree means we have no environmental temperature. There's no thermal noise. T 0 degree Kelvin, we have no noise. Sorry, but it's clear. 0 Kelvin or 0 Kelvin. It's means the world doesn't exist in this moment, and so it's only, let's say, it's not a real value what we can achieve. We can go down, for instance, to 10 Kelvin or to 20 Kelvin, but not to 0. B again is the equivalent noise bandwidth. We will discuss next lecture in more detail about this B. It's not only the bandwidth what we measure. For instance, if you look to a small band receiver or a selective receiver, which has a certain bandwidth, which has a certain steepness of the, let's say, edges, to receive or to amplify wished signals and to keep out other unwished signals, distortions, and so on. This bandwidth of such an amplifier, it's not the same what is meant here. And the available noise power is independent of the source impedance if it's matched, but only under this condition. But all formulas, what you are seeing here, has a base that the available noise power, it's looked or as matched, means we have no reflections between the source and between the receiver of the noise power. Now we can see here the nowadays used definition of noise figure came in the popular use in the 40th year of the last century. And the name of this man was Harold Fries, and he defined the noise figure F. You can find this F as a linear scale expressed noise figure, or in a lot of cases as a number given in dB. But we have to be very carefully if you apply this F in dB or in linear scale. Yeah, this is here the definition of the noise figure developed by Harold Fries. And what is the base? You can see here it's a relation of two relations. We have the signal of the incoming signal regarding or divided by the incoming noise power. Signal means power. This is the incoming signal power divided by the existing incoming noise power. This is divided by a relation of the outgoing signal power, in a lot of cases amplified amplified signal and divided by the noise power at the output. Or in other words, a quotient of signal power divided by the noise power at the input, and the signal power divided by the noise power at the output. We have here a relation of an input signal to noise ratio by an output signal to noise ratio. But be carefully with the noise power at the input or received by input. This noise power, it's the noise power which can your receiver only see at his input because of a lot of, let's say, frequency limiting elements, filters, the antenna, and so on. It's not a noise power which goes to infinity, what I mentioned before. No, this noise power, it's limited by the bandwidth of the complete receiver chain. So at the input, the noise power can be a little bit larger, but this is at least the noise power which goes defined by the bandwidth of the complete receiving chain, receiving system, determined at the input, and the same bandwidth is valid or its existence also in case of the output. But this noise power, it's not the same like here, because the bandwidth could be the same or is the same, it's clear. But again, you have inside your receiver amplifiers which also amplify the input noise and additional delivers a noise coming from the current flow of the active elements. And so the noise at the output, the noise power at the output is not only the amplified terminal noise of the input, no, it's also the terminal noise amplified by the elements plus an additional noise. And this is shown here. And then I it's the end of my discussion. You can see this, the same formula, what I have told here. And here you can see this additional noise coming from the active elements produced by the current flow. This G means power amplification, and here it's clear input noise power multiplied by G because of the amplification, but we have here this additional noise, and this makes the problem of our receiving system, namely the noise added by our device under test, and for instance, amplifier, and this G is the gain of our device under test if we only look to an amplifier. So now we come to the end, and thank you for your attention. And again, next Tuesday we have the last lecture, and I don't know, it's a decision of Dr. Hartmann. My suggestion was to make the examen on the Tuesday in 2 weeks, but we can change it a little bit. Depends on your situation. I can change it to, for instance, Wednesday or to Friday. Okay, thank you again and have a nice evening.
Goodbye. Thank you.
Thank you. Goodbye.